Okay. Okay, so now let's just talk about some signal properties. So signals can be either analog or digital. In this class, we mostly talk about analog. And then near the end, you guys might talk about like the sampling theorem. So that kind of like bridges the gap between analog and digital signals. And then the support is the smallest continuous time interval that contains all non-zero values of the signal. So it basically like measures how like precise a certain signal is. That's important when you're converting analog to digital. And then periodicity is another property that we're interested in. So if there exists a t greater than 0 such that x of little t plus big T equals x of t for all t, then a signal is periodic. So basically, if there's a certain big T where the signal repeats itself, then that's the definition of periodicity. And then there's something called the fundamental period. So for example, like sine of x, that's periodic every like 2 pi, right? But it's also periodic every like 4 pi and 6 pi and 8 pi and so on. But for that case, the fundamental period would be just 2 pi. That's the smallest. And then when you sum two periodic signals together, that sum is also periodic if the ratio of the periods between those two signals is a rational number. And then someone asked, will the recording be posted? Yeah, it'll be posted on YouTube later. And then we're also interested in even or odd signals. So an even signal means that x of negative t equals x of t. So that means it's like symmetric across the y-axis. An odd signal is when it's symmetric again across like both axes. So the definition of that would be x of negative t equals negative x of t. And then every signal can be expressed as the sum of its odd and even parts. So you can actually like extract the even component and the odd component using these two equations here. And if you do that and you add the two components together, then you'll just get back the original signal. And then another measure we're interested in is energy and power. So if a signal has finite energy, we call that an energy signal. And if it's finite power, we call that a power signal. So a finite energy signal is usually something that like decays like an exponential that goes down, like a transient. And then an example of like a power signal would be something that's like periodic, like a sine wave. Like that is infinite. That has like infinite energy because it goes on forever. But if you look at just a single period, then it's the power is finite. And then those are just the two definitions for those two things.
Yeah, so my advice is to think of this more intuitively. For example, with the energy, you can kind of relate it to things that you see in your circuits and your physics classes. If you think about electromagnetics, you might learn that like the energy is the square of the electric field or the square of the magnetic field. And so this is kind of a more generalized and mathematical way to think about it. If you learned in circuits that like the power being dissipated on a resistor is I squared times R or V squared over R, it's kind of the same thing, only like say you have like a unit ohm resistor. And then for the power, I also think it's kind of worth adding, you're basically like taking an average over the energy. It's a time average. And so you probably remember from physics type classes that power is just energy over the time. And also about the limit, that's kind of like a way to generalize this for like non-periodic symbols or signals, sorry. So yeah, for like a nice sine wave or something, you just plug in your t.
Yep, okay, thanks, Aaron. Okay, so these are just some important trig identities that you guys might want to know for your exam. So I don't know if you guys get a cheat sheet, you can just use your notes, but you should have this like somewhere, so it's like easy to reference. So the first two equations basically break down cosine and sine. And this is useful for like Fourier transforms or Fourier series, where you might need to like integrate. And it's easier to integrate after you break it down into these forms, as opposed to just leaving the cosine or sine in there. These two expressions are also pretty useful for the same purpose. A lot of times you might get like, you're trying to integrate like cosine square or something. So it'd be easier to break it down first before you do that math.
Another really good trig idea is the like product ones, like cosine, or I guess some formulas like cosine A plus B. If you have a cheat sheet, those can be pretty nice sometimes.
Yeah. So there's a couple of special signals that you learn in this class that are really useful. So the first one is the delta function, or the Dirac delta. So important properties of that. Well, by definition, first of all, the Dirac delta is negative infinity at, the delta function is, it's infinity at t equals 0, and it's 0 otherwise. And usually you don't just like use the Dirac delta by itself, right? Because it's infinity, so it's like kind of meaningless. So the way you use it is usually like you use it to integrate or something. So another important property is that the integral of the delta function from negative infinity to infinity is 1. Okay, just undefined. Yeah, I guess it's undefined or infinity. You don't really call the delta function by itself anyway. So yeah, undefined. And the sampling property, yeah, it's also pretty useful. So as I said earlier, like you guys probably learned about the sampling theorem. So you basically like have a continuous time signal and you use an impulse train, which is like a series of delta functions, and that's how you like generate a discrete signal. Another important thing is the impulse response function, h of t. And this basically describes like a particular system that you pass a signal through. And by definition, the impulse function is the output of a system where you apply the delta function as the input. And this is really important for the analysis of LTI systems, as we will see later. And for LTI systems, the output for an input x of t would just be the convolution between x of t and h of t. Some signal system properties, sorry. So these are like the LTI, those type of stuff. So a system is time invariant if you delay a particular input by t naught and the output gets delayed by the exact amount t naught. And linearity means you can have a superposition of two inputs and the output will also be the exact same superposition. And then an LTI system, by definition, is both linear and time invariant. And it can be defined by the impulse response, which we just mentioned. And basically, what makes these unique is that it doesn't create any new frequencies in the signal, and it only amplifies or attenuates. So essentially just like scales the, if you scale the input, the output will be scaled the same way, basically. And it won't like change like the overall shape or anything. Causal system means that at output time t1, it only depends on x of t for t less than or equal to t1. So basically the output only depends on present and future values. And then another important property for that is that in LTI and causal systems, the impulse response is defined by h of t equals 1 for t less than 0. So the impulse response only has values for t greater than 0. System is BIBO stable if the input, both the input and the output are finite values. And then if the system is BIBO stable and LTI, then you can see that the integral of the impulse function from negative infinity to positive infinity is finite. So that means like the signal is, if you feed like any signal to the system, the signal won't like reach infinity and like explode or anything. So this is really important for like practical systems. You don't want to create something that's unstable. So the convolution is a operation that you can perform on signals. So some basic properties, it's commutative, so you can change the order that you use the operation on. It's associative, so you can like move like the parentheses around, and then it's also distributive. So if you have like, well, that's self-explanatory. And then another important property is the sifting property. So if you have a signal x of t and you convolve it with a delta function located at time a, then basically you'll produce a shifted version of the input signal by the same amount. That's the definition of the convolution. Yeah. So you guys probably learned this, like this is like a flip and slide trick. So you probably won't be doing this on the final. If you find yourself having to do this, you might be doing something wrong because later when we talk about LTI systems, there's a way to like get around doing this. This is kind of tedious. Next, we're going to talk about the Laplace transform. So in this class, we learn about the unilateral or one-sided Laplace transform. So this is the definition here. And the reason it's one-sided is because the function only exists for one side usually. So usually if you have a signal, you multiply it by like the unit step so that the values only exist for t greater than 0. Another important thing about the Laplace transform is that there's a region of convergence associated with the Laplace transform. And it basically defines the bounds of the real part of S where the integral converges. And so basically when you find the transfer function in the Laplace domain, you'll look at the poles in the function, and then you'll pick out those poles and shade in everything like to the right, and that would be the region of convergence. So this is like a more mathematical way of looking at it. So if you have like some transfer function here, if the degree of P is less than the degree of Q, then you're good to go. You can just extract the poles from there. Otherwise, if the degree of P is greater than the degree of Q, then you'll need to first divide it using like long division until the degree of P on top is less than the degree of Q. And then you can find the region of convergence from there. So the region of convergence is the real part of the S-plane greater than the rightmost pole. This is like a table of the Laplace transform pairs. So these are like some really common functions that you'll use throughout this class and in later classes. So you guys should also definitely have this when you're taking the test, because you don't want to be doing every single Laplace transform by hand, doing the integral and everything. So make sure you reference this. And then these are the transform properties. So this goes along with the previous slides. So you should also have this. And basically you should be able to answer like a lot of the questions just by using these properties in these pairs. And we'll have some examples of that later. So earlier I mentioned that LTI systems have some important properties to them. And I also mentioned that like for convolution, you shouldn't be, like flipping and dragging or like computing the integral every time, because there's like an easier way to do it usually. And this is like one such example. So if the problem tells you that the system is linear time invariant, then instead of computing the convolution between the impulse response and the input, you can simply multiply them after transforming them to the Laplace domain. So this is just like a proof of why that works. So you start off like the output y is the convolution of h and x, and then you go through some steps, and then later you'll find out that you can just multiply the two, and you'll get the output. Another important thing is combinations of systems. So if you have two systems in cascade with each other, or in series, then you'll find that the overall transfer function that describes both of them is simply just the product of the two. So you can just say like z of t, or sorry, z of s equals h1 of s times h2 of s times the input x of s. And then when you have systems in parallel and they add up using like this sum block, then you can just add the two impulse functions together to get the equivalent. So you see here, like there's h1 of s plus h2 of s. That's like the left-hand side, and then it gets multiplied by h3 of s because they're cascaded. Another important thing is the eigenfunctions. So this makes it easier to compute the output for certain classes of inputs. So one such class of input is the exponential. So if you have a complex exponential, e to the s naught of t, then you'll find that the output is simply the product of that exponential input times the transfer function evaluated at s naught. And then the same can be said for sinusoids. So if you have a sinusoidal input, then likewise, the output will be simply the input scaled by the magnitude of the transfer function, and then phase shifted by the phase of the transfer function. So this is really powerful because you normally wouldn't think that you could combine like Laplace domain expressions and time domain expressions, but this allows you to do that. And it simplifies the calculations by a lot. Okay, so now I'm going to talk about the Fourier series. So basically, the Fourier series is a way of decomposing a periodic signal into its individual. A Fourier series decomposes the signal into its fundamental exponential terms. So you see here on the bottom, it says f of t is the sum across all n of f of n times this exponential term. So this exponential term is like the basis function. Basically, a periodic signal can be broken down to like a sum of exponentials. Right? So the exponentials are the bases, and then these fn's in front are the coefficients. So if you think of like an xy coordinate axes, right? The x-axis and the y-axis are the basis, and then the actual values of the points, right? Those are like the coefficients. And then the point itself would be like f of t, right? So like you're breaking down a point into coefficients and bases. And the way you compute the coefficients of these bases is by using this top formula here. So big F sub n, those are all the coefficients of the Fourier series expansion.
Another pretty simple way to basically say what a Fourier series is it's a way to represent any periodic symbol, or sorry, keep saying that, any periodic signal. And you can do it with just sinusoids and sines and cosines, basically. The complex exponentials are also another form of sine and cosine. You can really do it with any basis, like Vincent's saying, but
okay. So some simple properties of the signal of the Fourier series. First, Fourier series is linear. So for signals with the same period and finite power. And there's also these important symmetries, right? So let me write down the cosine expression again. So cosine of x equals 1/2 e to the jx plus 1/2 e to the negative jx. So this is f of x. So f of 1 is half, and f of -1 is also 1/2, right? And the subscript of the f is basically like the coefficient in front of, it's the coefficient in front of like this g of x here. So this is 1, this is -1.
It's like a harmonic of the fundamental frequency.
Yeah, right. So cosine itself is like it's called like the first harmonic because you're doing like index 1. So if you look at the property here, right? If x of t is real, then c of negative k equals c of k complex conjugate, right? So that's true here, right? Obviously, f of 1 is the complex conjugate of f of negative 1. And then if x of t is even, then c sub k equals c sub negative k. Cosine is even, and you can see here that they're the same. And if x of t is odd, then you get c sub k equals negative c sub negative k. So for example, sine of x is odd, right? And we can express that as this. So here f sub 1 is 1 over 2j. F sub negative 1 is negative 1 over 2j. So clearly here you can see that, so if you follow here, like f sub 1 is the negative of f sub negative 1. So you can see that's true. And then there's also time shifting. So if you have the Fourier series coefficient of x of t is, yeah, sorry, all these are in like discrete notation, but just c of k is the same as f of n. Yeah, this is a different notation. But let's say x of t has a Fourier coefficient f of n, and if you time shift it by t naught, then the new coefficient for that is just a time shift, sorry, an exponential multiplied version of that. And then if you time reverse the signal, then the new Fourier coefficient would be, you take like it'd be like reversed, right? So the new coefficient would just be the same, but reversed. And then there's time scaling. So time scaling does not affect the c sub k, because it simply just like scales the function, doesn't change like any frequency components, right? So that's what this is saying. Okay, and then Fourier transform. So this is closely related to the Fourier series expansion, except for the fact that the Fourier transform can be applied to any signal, regardless of whether or not it's periodic. That's the reason it's more widely used. And a sufficient condition for the Fourier transform to exist that the integral of the magnitude of the signal from negative infinity to infinity is finite. So as long as it's a finite signal, then its Fourier transform is sure to exist, regardless of whether it's periodic. And these are the definitions. So you'll find that they're pretty similar to the Fourier series equations, except now instead of having like t, you have like negative infinity. So you can basically imagine the Fourier transform equal to like the Fourier series if you take the period to infinity. So if you do that, then you'll get like very similar expressions. So here are some properties, pretty similar to Fourier series. Linearity applies here. Inverse proportionality with time and frequency. So these are just like the properties that you have like in your table. It'd be good to have this on the test. If you time shift again in time domain, you'll get exponential in frequency domain, and likewise the other way around. There's also some symmetry properties which are similar to the ones we talked about earlier. I'm not gonna go through these. Just make sure you have these on your cheat sheet or notes, and because it's really easy to make like true, false, or multiple choice questions out of these. Like they'll give you a signal and they'll ask like, which of these is true? Like it's real, it's even, etc.
A small comment on studying for the exam. If you get like computational problems, it's really useful to have these on your cheat sheet, obviously. But a lot of professors in signals are pretty fond of like proof type problems. And they're not going to give you a property that's on your cheat sheet. But if you do go through the proofs that you see here and in the last few slides, I feel like it really helps you kind of get comfortable with the mechanics of actually like proving new properties. So it's worth doing a few of them if you have the time and the drive.
For sure. Okay, these are just some more properties. So this one we already went over, right? The convolution time domain will indicate a multiplication in the frequency domain, and the same is the other way around, right? So you notice like a lot of these properties are like invertible, so to speak. Like you can go either way, and it's like the same. And that's like a result of what's called duality. So basically, moving between the time and the frequency domain, like you can move between the two, and moving either direction like produces very similar properties. Yeah, it's just some more properties. Differentiation. Also mentioned this already. Yeah, and then duality, as I said, you can move between the two, and it's the same either way. So this is just a table of the common properties. A lot of them we just mentioned. I'm sure like the professor gave you a table or something, so just make sure you have that on the test. Okay, let's just do a simple problem here. So this is a pretty like canonical problem in Fourier transforms, and it's like a really important transform too. So we're going to start with S of omega equals rect function. So the reason this is, well, one application of why this is really important is later on you learn about like low pass filters, and this is like a really useful function for that, right? So if you have like some signal with like this kind of Fourier transform, and you want to like only allow like low frequency signals, then you'd put a low pass filter on top, right? And that will like cancel out all the other high frequency components. So this will go away, this will go away, right? And this low pass filter is basically just like a rect function, right? That's one common usage. So we want to figure out what the time domain representation of the rect function is. So the inverse Fourier transform, the rect. And of course, like on the real test, you wouldn't want to actually do this by hand. Like I'm just showing you like, because I want to like walk you through one example, but if you actually need to find the inverse Fourier transform of a rect on the test, just use the table and you go directly to this. But I'm just showing you for this example. So let's just write the definition of the Fourier transform. So check. So 1 over 2 pi omega of negative infinity to infinity. Okay. Okay, so let's plug in the rect function. So the rect function is basically has a magnitude of 1 in the range of negative alpha or negative a to positive a, and then 0 otherwise, right? So basically you can change the bounds of the integral to just negative a to positive a. Magnitude is 1.
A way you can always remember that with the rect is for the signals classes. The rect is defined as having unit area. So so that's why like basically if you plug in 1/2 to the rect, you get 1. It's because you want to have a unit area rectangle. And then when you start playing with the arguments, like stuff like 2a, just remember like the time stretching and compression properties. Then make sure to check out your definition of triangle, because that probably also has unit area. But yeah, just double check. It's a pretty good way to remember the shapes.
Okay. We integrate the exponential term with respect to w or omega. Get that. E to the so you notice it starts kind of looking like the sine expansion, right? So let's try to get into that form. T over 2j. So there's like this a term in the exponential. So let's try to get that in the bottom. So we multiply top and bottom by a. So now this is just sine of at. So this whole thing just becomes a over pi t sine of at. And you can just rewrite this as a over pi sinc of at. So I'd also check out the definition of sinc, because that's also varies quite a bit. So here I'm defining sinc at as just, that's totally wrong, as sine of at over t. But some people might call it like sine of at over like at, or like sine of at over like pi t or something. Like there's a lot of like different expressions. So make sure you're clear about how that's defined. And usually like they tell you on the test. Okay, so that's, I'm just showing that really common example with the Fourier transform. So another thing you guys learned, the Parseval's identity. So this is useful for calculating like complicated integrals. So like if I asked you to compute like the energy of a signal, like that would be the right hand side, right? You compute like the integral of the magnitude squared. An easy way to do that is just by computing the sum of all the Fourier coefficients squared. Because sometimes like it's not feasible to compute this. So if you break it down to the Fourier series expansion, then you can compute this energy a little easier. This is a similar thing, Parseval relations. So those previous examples for the Fourier series expansion and the coefficient C of n. And you can also do the same thing for the Fourier transform. So it's basically saying, this is basically saying that like the Fourier transform preserves energy. So the energy in the time domain is the same as the energy in the frequency domain. So this is like a small example of how it's used. So if you're asked to compute like the energy of a sinc function, like you'd plug that into the integral and it'd be like sinc squared. And you could like try integrating that, but it'd be like extremely difficult. So an easier way is to transform the sinc into the Fourier transform representation, which is rect. And then you can like compute the integral much easier that way. Okay, so sampling theorem. I think this is the last topic. So sampling theorem says that when you're trying to convert from analog to discrete signals, you use an impulse train to capture samples of the analog signal. And this says the impulse train in the time domain corresponds to the impulse train in the frequency domain with different spacing and weighting. A continuous time signal with frequencies less than or equal to omega b can be perfectly reconstructed from the samples provided that the sampling frequency omega s is greater than or equal to omega b. Right, so basically this is like the criteria in order to properly like reconstruct a signal. So if you have some signal and the highest frequency in that signal is omega b, then your sampling frequency needs to be at least 2 times that highest frequency in order for the signal to be reconstructed accurately. And that threshold is called the Nyquist frequency. It's also important to note that signals that are discrete in time are periodic in frequency, and signals that are periodic in time are discrete in frequency. So for example, I showed you like the cosine. So cosine is periodic in time. And then when you break it down to its Fourier series coefficients, you saw it was like 2 delta functions, right? So it's discrete in frequency. And then aliasing is a term to describe what happens when you don't have a sufficient sampling frequency. So if it doesn't meet this Nyquist frequency criterion, then it will result in something called aliasing. In that case, like you won't be able to obtain the original signal from your discrete values. So I'll show an example of that here. So here, the green signal is the time domain representation. And then these little peaks at the bottom, I don't know if you guys can see this. I like the little peaks in the box. So this lower line is the Fourier transform of the signal. So in this first example, you're sampling at 48 kilohertz. And in this signal, the highest frequency, FB, is 19.5 kilohertz. So clearly, 48 kilohertz is more than 2 times of 19.5. So in this case, you're good to go, right? You can see, like in the Fourier transform, you can still see this 19.5 here. But then if you use like a lower frequency, like 24, so 24 is not greater than 2 times 19.5, right? So that means like you'll end up losing this 19.5 kilohertz signal. So like if you look at the Fourier transform here, the 19.5 kilohertz peak got like shifted all the way down, right? So like it like interpreted that signal wrong because you didn't have a high enough sampling frequency. So you can see here, like in green, the time domain function is like a lot smoother, as opposed to like when you use a higher sampling frequency, the function is like much rougher and you can see like more detail, right? So this didn't capture enough detail and then it got this signal wrong. So that's why it's important to choose a sufficient sampling frequency. So this is just a summary of everything we've discussed. So we have time domain analysis. So we use that for like ODEs, convolutions. That always applies, but the reason that we don't use it is because it can take a long time doing like integrals and convolutions and stuff. Then we introduced the Laplace transform. This works for unilateral functions, meaning that it only exists for time greater than 0. It can be used to study transients and stability. We talk about like the S-plane and how to determine if something is stable based on the location of the poles. And then we introduced Fourier series and transform. So Fourier series can be used only for periodic signals, while Fourier transform is more general. It can be used for any finite signals. They're both used for steady state analysis. And yeah, generic signals. Okay. So I'm just gonna end on like a practical application of all the stuff that we learned. If you're anything like me, at the end of this class, I was kind of wondering like when I'd ever use any of this stuff. It was just like, I feel like it's just like a ton of math that like wasn't very practical. So I'll show you guys like some like how this stuff is used in real life. So if you guys ever listen to radio, you've probably heard of like AM radio. So AM stands for amplitude modulation. And this is like a really common way that signals are transmitted across the air. So if you look at this system diagram here, X of t is like the signal that the radio station broadcasts. The signal gets mixed in with some cosine to form S of t. And S of t is what gets actually sent across the air here. And then this side is like your radio receiver. So you receive the signal R of t. That again gets mixed with some cosine function. And you receive Z of t. And then you put that through a low-pass filter, and then this is what goes out your speaker, right? Y of t. So like how exactly like, does all that work, right? So, so you start off with the transmitted signal. S of t equals X of t times cosine of omega t. And then if you take the Fourier transform of that, the Fourier transform of the cosine is two delta functions, right, at frequency omega naught and negative omega naught. And you convolve that with the original signal, right? So then you get like this expression here. So like, let's take a look at like what that exactly means. So so this is like the original signal that you send, x of omega. So this is the Fourier transform of the original signal that the radio station sends, right? So this is like pretty low. This is like on the order of hertz, right? But then when you turn into a radio, you turn into like some channel that's like 700 kilohertz, right? So that that 710 kilohertz is actually not like the frequency of the sound you're hearing, right? That'd be really high. The frequency of the sound is actually really low. It's on the order of hertz. But then you want to transmit that to a station where it's very high, like on the order of kilohertz. So then that's what S of omega is, right? So you have S of omega. That basically forms, it shifts the radio sound into the kilohertz range, right? Like this term corresponds with this. It's like the input shifted by omega naught. So this is omega naught. This is negative omega naught. So now this is like the frequency domain representation of what gets sent out across the air. Then you receive something pretty similar here. So you see R of omega is C times the expression. So like when the signal gets sent over the air, like it might get like attenuated or something, but the frequency should still remain, right? So you receive something at the same frequency, but like slightly attenuated or something like that. Okay, so now this is what your radio sees, right? But you don't want to hear this, right? You want to hear like the original signal that was sent out, like this thing, right? So how do you get that back? Well, you mix the received signal with another cosine, and then if you look at the Fourier representation of that, I'm just going to copy this line here. So it's going to be C over 2 x of so if you work out the math and take the convolution between these two and apply like the sifting property and everything, you'll find that this is the signal after it gets processed by the cosine again. So now it's at these two even higher frequencies, 2 omega naught. And you also get like this big signal in the middle, right? So now this is the original signal that you want to hear. And the two like side lobes are like these extra like high frequency things that you don't want. So the very last step is just to apply a low pass filter on top of this middle thing, right? That eliminates these two. And then this part is what you hear through the speaker of the radio. So that's just an overview of like how an AM radio signal will work and how it's passed through the air. You obviously don't have to know this for a test, but I just thought this might be interesting to some people if they're wondering how this is used. Okay, I think that's about it. Do you have anything to add, Aaron?
Not too much. Yeah, I mentioned something in the chat to you, but yeah, in general, I definitely I would go through some of the proofs for the properties you see. Again, it's mostly like kind of massaging the Fourier transform equation and stuff like that. So like be strong with identities, and of course practice a few problems, but yeah, like don't forget the theory.
All right. Yeah, I mean, I think you guys don't get a cheat sheet, right? But you guys can use your notes and everything. So, yeah, my recommendation would have been just putting everything in your cheat sheet, but you guys don't have that issue anymore. I'd say just like be really familiar with the tables. Like obviously you can reference them and everything, but like it's good to like when you're doing the homework to like be really familiar with all these so that when you're taking the test, it comes like really natural.
But yeah, likewise, yeah, definitely use the table as much as possible. I don't know. I've personally like had, this is just me, like sometimes I've had a problem where like, I don't know, the table is just like kind of awkward to use for like a few functions. You could give a shot just like directly plugging it into the equation. Just like remember that's always an option if like you somehow get stuck or you can't use the table.
Yeah, and then if you do have to resort to that, and you have to do like some really long-winded computation that takes like 2 pages, and there's probably an easier way to do it. So like we mentioned all those at the beginning. We mentioned like the trig identities. So yeah, these are things you could use. Yeah, just be like on the lookout for those kind of simplifications or tricks, because there shouldn't be like just really long computation problems. Yeah, I don't have much else. Yeah, I guess we'll stick around if you guys have any questions. That should be it for us. I'm gonna stop the recording.